Good afternoon, everyone, and thanks, Ting, for that introduction. So I'm here to present our paper today, so towards incorporating human knowledge in fuzzy pattern tree evolution. On behalf of myself and my team, so that's Grainne Murphy, Douglas Mota Diaz, Jorge Amaral, Enrique, Naredo, and Conor. So we're all part of the BDS lab in the University of Limerick, with Jorge and Douglas also being part of the University of Rio in Brazil. Okay, so our paper sets out to empirically prove that these structures, fuzzy pattern trees or FPTs, that we used GE to evolve can be considered a powerful XAI system. So we'll go into the kind of criteria we set and how they move. So we compare them, again, their accuracy against other machine learning techniques such as random forests, just to kind of give you an idea of maybe the trade-offs you're getting. But then we also go one step further. So we give these best of run models to an expert, and we ask them to score on two criteria. One, their interpretability. So can't you kind of understand? And second is their logic. So are they overfit essentially, or could you trust this model if it was in the wild? And we saw from previous work that these can tend to kind of bloat a little bit. So we use various approaches to try and mitigate that. So we saw that the models that the expert had deemed interpretable and trustworthy, so kind of coherent logic, so they were seen to outperform interpreted models which had poor logic. So essentially, she was able to identify overfit models, kind of validating the interpretability. And then finally, we just looked at the depth at which these FPTs were kind of seen to lose their interpretability to kind of guide future trust. So last 20 or 30 years, there's been a huge explosion in kind of ML applications and specifically learning applications due to huge computers and then vast amounts of data that kind of can be stored cheaply and then accessed very, very widely. So this has kind of spawned huge industries and success stories that have crossed over from just kind of conferences like this, but also you'd seen written about in the BBC. You know, you'd always see articles written about maybe Tesla or Forbes, something like that. So these learning algorithms are usually very successful in prediction, oftentimes matching or exceeding maybe human performance in the task, but they do come with the lack of insight. So there's no way of knowing, has your model maybe broken any rule somewhere, or if you give it some data, is it actually outside of the scope then it was trained? So there's no, if you had a human computing this task and you'd wanted to have this common sense, there's just no way of saying that the machine or the computer actually has that. So these are the kind of, you know, the black box models that everyone kind of talks about. So the big trade-off they have is that you can't establish trust. So there was a very famous, or I guess infamous example of this in America, where they had this system that was looking at people who are convicted of crimes. And if they were up for parole, they had an AI system which tried to predict if they would reoffend again. And this was found to be incredibly biased against Black people unfairly. And this was going unchecked for years before it was seen. So again, there was no way of getting trust in that model before it actually went out. They just had to rely on its training accuracy. So kind of even moving on there from the real world and actual scientific context, you can't gain any more knowledge. So once you kind of train the model, you can't look at it and see, is there any relationships that it found that you could maybe investigate further or kind of give you any new information that you didn't already know. You just have kind of these input-output pairs. So this corresponded a new branch of machine learning, which is very popular these days, Explainable Artificial Intelligence, or XAI, which you can kind of maybe broadly class into two areas. So kind of global, where you're maybe trying to explain a model, and then local, where you're trying to explain a decision. So if you give it some data, it will say why it was classed as such. So here we will be talking about global explanations. So we'll be trying to explain models, but just kind of be aware that there are other techniques. But regardless if it's global or local, the overarching goal is, okay, can we build AI systems which can explain themselves, or if they can't explain themselves, at least give us a way of interpreting their results. So there are several keys to kind of explainable artificial intelligence. One is that they need to be unambiguous. So you have multiple people looking at this, that they all get the same logic, or they all get the same information, that they aren't kind of guessing. The second is they need to be in a form comprehensible to humans. So obviously if a human can't read it, it's no good. And then finally, they need to be competitive with kind of traditional black box. So again, depending on what area you're in, you usually will be willing to sacrifice some accuracy to gain that interpretability, depending on your area and stuff. But again, you still need to be within the kind of range that the black box accuracy is getting for it to be a useful system. So to solve the first point, we adopt fuzzy set theory. So instead of giving humans variables with maybe kind of random cutoffs, like you'd maybe see in a decision tree, we're giving it to them in linguistic terms that they would be useful. So kind of language that they would be used to dealing with this data with all the time, that they're used to seeing. So kind of stuff is low, is this variable high, is it medium? So this immediately gives these models kind of high degrees of interpretability because you're dealing in natural language that humans are used to processing every day anyway. So secondly, they need to be in a form comprehensible to humans, and that's where a tree structure that we would see. So this does two things. The first is it kind of mitigates the problems that are you kind of associate with fuzzy rule-based systems, kind of meaning if you give it more data and the more accuracy you want to get, you need to increase the number of rules exponentially. And of course, the more rules you have, you're losing interpretability with every rule. So when you're representing it as a graph, you kind of leverage a human's ability to recognize patterns. So they can kind of follow how variables maybe interact with each other and how they flow within the decision in the tree more easily than if you just presented them as kind of sets of rules. So actually looking at the trees and the patterns kind of gives you the best of both worlds, that you can add a little bit of more complexity without losing that interpretability. So when you kind of combine these two things, so fuzzy representation and this tree structure, it gives you these fuzzy pattern trees. So as I said, they're a tree-like structure whose nodes are fuzzy logical and arithmetic operators and whose leaf nodes are fuzzy variables. So you take your data set and you fuzzify its variables. Those are your leaf nodes, and then the inside of the tree are the fuzzified operators. So like you'd see in a regular GP tree, takes information from the bottom all the way to the top. And because your inputs are 0, 1, because they're fuzzified, and all your operators are 0, 1, that gives you an output between 0, 1. So each tree will give you a number between 0 and 1. So to go from just what is a fuzzy pattern tree to building a classifier from a fuzzy pattern tree, you first need to create one FPT per class. So if you are binary classification, that would be 2 trees. If you have multi-class, it'd be 3, and so on and so forth. So what you do is you give each data point to the tree. They output a score, and whichever tree has the highest score wins, and then we classify that individual as that class. So here's just an example here where we have this furthest right point here. It's given to our trees F1 all the way to FC. So tree number C has the highest score, so that wins. So this individual would be classed as class C. So what this allows us to do is that each tree can therefore be considered the description of the classifier. So the kind of a logical description of the class. So this is the interpretation of what that class is trying to do, or what the classifier is trying to do. So just kind of a quick illustration here. So one of the examples we did is the heart disease data set. And this is an example for the presence of heart disease. So it's okay, it's strongly determined by 3 criteria. So the first is we have this thallium stress test that found a defect. The second is that this fluoroscopy found a moderate number of vessels. And then thirdly, that this ST segment, that the slope of it was flat. So filling in the rest of the tree, we can see the criterion 1 and criterion 2. So the stress test and the thallium stress test and this fluoroscopy contribute roughly equal. We have the weighted average is around 0.5. And then criterion 3, so the slope of that test contributes about 16%, so a not insignificant effect. So this is kind of an example how you would interpret a tree. So you could give this to an expert and see, does this make sense? Would you associate these results with these tests resulting in a heart disease decision? Okay, and then finally, the last point, that we need these to be competitive with black box models, and this is where grammatical evolution comes in. So GE is an evolutionary search technique which uses a grammar to create a program in any arbitrary language you want. And crucially with GE, it's flexible. So we have the flexibility you'd associate with most EC techniques, where you can specify your fitness function, you can specify your selection procedure, stuff like that. But also GE gives us the grammar, which allows a lot of flexibility when you're moving from kind of problem to problem. So it best allows us to find accurate models, but at the same time trying to keep them explainable. So combining all these together, we just have fuzzy GE, or FGE as we will call it in the rest of the paper. So this is an example of what our operators we would use here, the fuzzy operators, and this is an example of a grammar. So just to note here that although we are evolving multiple trees, the way this is set up, we don't need any special operators or protected operators or anything like that, because we specify it in the grammar here. So you can see here that we have this kind of winner take all node, which is our decision node. And here we have it set up for binary classification. So we have two EXP non-terminals here. So that's evolving two FPTs essentially. If we wanted to make this multi-class classification, all we would need to do is add another EXP non-terminal in that class. So you could maybe think of it that we're evolving one tree with loads of subtrees, which are FPTs, which maybe graphically would look like this. But essentially we're evolving FPTs n number per class. So our experimental setup, we just used root mean square error for our fitness with 1 minus guiding our search. And then we also wanted to set up two experiments to try to restrict the size. So the first was just a soft penalization of large solutions. So just getting its max depth and then penalizing the solution like that. And then the second was a hard penalization where we just set a limit at which we want these trees to go. So we set it here at 3. And the reason we chose this was in our previous experiments, we saw that almost no trees were getting to this depth. So in order to give these trees to the expert, we wanted a kind of a full setup of depth. So we could get a full depth to give to them to get a better understanding of where does depth fall off and stuff like that. So again, it's not the most subtle of fitness functions, but again, we just wanted to restrict the size a lot. So here's our experiment. So we did 30 runs of each. And aside from tournament selection, we also used double tournament selection, where the first we did a tournament on size, then fitness, and then we switched it around from fitness to size. And we used effective crossover and sensible initialization. So once we had that done, we didn't stop. So we sought out an expert to actually validate the interpretability of this tree. So this was a doctor in a local hospital, and we gave them the heart data set. So we got our best of run individuals, we parsed them into trees. So that would be 150 total. So we had 5 experiments at 30 runs each. And then we asked the expert to score them on 2 criteria. So the first was the interpretability of the tree. So can you read this tree and understand what's going on as just a human, I guess. And then secondly, the logic. So using your expertise, would you, if you were making this diagnosis, use these parameters in this context? Or are they essentially overfit, or it doesn't make any sense, stuff like that. So we, aside from the heart, we also use benchmark problems just to get a sense of the accuracy, but we didn't give them to an expert, but just to kind of give an expert of what kind of trade-off you might expect. So these are all real-world problems. And these are often used in XAI benchmarks because they will contain one or more, they're called kind of protected classes. So for instance, here we have the pro-Republica recidivism ones. That's the actual data set that the people used in the article I showed you earlier about the kind of the racist AI essentially. So again, these are things that really could do with a human in the loop, and they kind of need human oversight to kind of check themselves. And we did 5 GE setups. So that's just kind of the regular grammatical evolution, the 2 parsimony pressure setups, and then the 2 double tournament setups. Then we also did a SVM random forest and logistic regression. So here we show our results. So this is our averaged test accuracy. So you can see that the random forest was the best performing classifier on every problem, which I guess is to be expected. However, we're seeing that FGE is only about 1 to 5% worse off than the random forest. So again, depending on your particular setup or your particular use, that could well be within your acceptable range without this kind of maybe expert tuning that we're trying to do later. But it does show you, just to put in context, that FGE is worse, but that gap is very manageable, I think, in my opinion. So moving on to just looking at the max depth of the solutions, and just to note here that the solutions underwent an intron removal process. So basically it just looked at the solutions, and that if you had something like we squared something, then square rooted it, obviously would return the original number. So we just removed them from our, we removed them from the individuals before we parsed them into the tree and gave them to the expert to try highlight or try increase their interpretability as we went along. So here we see, and I guess no shock, that the the harsh regularization was the smallest solutions. However, it's probably surprising how poorly that the double tournaments did, often bloating trees larger than just a regular GE without any bloat control. So again, going forward, it probably will need to be a slightly harsher regularization technique if going forward to use this in the future. So before we kind of show you our expert results, I'll just kind of show you when we say interpretability, what we're talking about. So we asked the expert to score it from 1 to 5, 1 being can't be interpreted, 5 very interpretable. So this is an example of a tree which got a score of 5. So we can see here on the left, we have the FPT here just has 2 variables, and on the right, we have an example here that has 1. So again, the depth isn't very deep, and again, it only has 2 variables and 1 3 on the other. And then here's an example which scored 1. So the expert said there was absolutely no interpretability, which I guess most people could probably guess. Again, just bloated, and although there might be variables in the right position, to try track them as they go up the tree and their interactions with other variables is just too much. So here present the interpretability score for each selection type. So the 1 to 5 that the expert gave for each tree. So we see it here. As we can see, the hash regularization achieved almost perfect interpretability, which I guess is to be expected. And we can see that the other had a large number that did score this one. Again, just too much bloat got in, and that they were, although maybe performed well, just can't be used. So for our next slides, what we're going to do is just focus on the trees that the expert said that she could interpret. So that means that she gave it a score of 3, 4, or 5. So either good interpretability or moderate interpretability. So she says she can interpret it, therefore her score for her logic would be founded because she can interpret what's going on in the tree. So splitting them out, what we see here in green and red. So what we have here at the bottom in green are models that the expert said she could understand the logic of the model and she's happy with her interpretability, i.e. that she could trust them essentially. And what we have here in the red is that models that the expert said she could interpret, but she wasn't happy with their logic. So i.e. they were overfit somehow. So they were using variables in diagnosis that she wouldn't as an expert use. So as we can see here, despite having identical training performance, that these models that the expert was able to pick out as being overfit are performing over 2% worse than the models that she said are performing good or better logic. And even then, if you want us to go further, so instead of just removing bad models, if you only wanted to include in good models, we're still seeing this improved performance in accuracy. So again, what we have here is a system that allows the user to apply their expert knowledge to remove overfit individuals from the search and use only models that she's comfortable using that she can trust. So then just finally looking at where does interpretability cease to exist, so at what depth. Again, hardly no surprise that it kind of falls off rapidly once you get to about depth 5 or depth 6. And after that, you're really getting nothing useful. So again, it's around here. So this might be different from user to user and depending on the expert and the situation. But again, going forward, we did all of this kind of post-run analysis. This is something we would want to include post-run so we could tailor our search towards this going forward. Okay, so just to sum up, we showed here that FPTs that we evolved using GE can be viewed as a very powerful XAI system. So although our results were very competitive, they were maybe that little bit off, but very competitive task. However, crucially, we are getting an interpretable model. So whatever knowledge was found during the learning process can be leveraged and we can present our results to users in a comprehensible way. So we examined this interpretability empirically and able to see that a domain expert was able to improve the performance of a system. So it wasn't just a case of her saying she could interpret. We actually proved that no, her interpretation allowed her to score the logic, and that logic was seen to perform better than poorly performed logic. Okay, so moving, like next steps will be probably trying to involve the domain experts in the step in the process more future. So obviously, in the middle of Corona, it was tough to try find a doctor to cooperate, a lot of spare time. But in future, kind of grammar design in terms of the selection, the fitness function, and maybe crucially in the max depth of the solutions. So again, if you're maybe designing on a depth, maybe something like DSGE might be better suited than GE, something like that. And then finally, the more maybe technical would be, how do we improve accuracy without compromising interpretability? So that would be looking at boosting, whether gradient or maybe adaptive boosting, ensembling, or I think what could be good would be encapsulation. So if you have maybe a concept that the user is used to working with or happy to working with, you can just encapsulate that into one node. So instead of dealing with something that might be depth 5 or depth 6, you could bring it all the way to depth 3 or depth 4, something like that.